lecture we have covered the different components of the load torques. This lecture I am starting with nature and classifications of load torques. Nature and classification of load torque. I am going one by one. The first one is graphical representation. This is omega axis, load torque. Now this representation is TL proportional to omega m square. Okay, that is the load torque. This kind of load torque is found in case of the motions opposed by the fluids or air. That is motion opposed by fluid or air. That is different applications are pump, aeroplane, fans, ship propellers, etc. Like this. Okay. Now number 2. For low speed hoist, where the load torque remains constant. This is a constant load torque. TL is constant. That is for low speed hoist. Low speed hoist. Okay. Next, for high speed hoist, where the friction due to viscous and air will be considered. That is this application is for high speed hoist. High speed hoist, where viscous friction and windage friction have considerable amount. Okay. Now coming to the next one, that is for traction. In case of traction, the entire mass have to overcome the static friction or friction. That is, friction as the considerable amount of friction is to be considered. Okay. And after overcome the speed, then air friction or the viscous friction will be dominating. That is, friction have to be considered. This is for the traction load. Where large amount of friction to be considered because of heavy mass. Okay, and after overcome the speed, then viscous friction and windage friction dominates. And next will be the constant speed operation. This is the load torque, where the nature becomes hyperbolic. Okay, such as this is constant power load, such as coiler drive. Okay, where it can be also defined as, say, coiler drive is like this. Say this is the linear velocity and linear force is applied on this. Okay, and this is the radius r, and motor is rotating at speed omega. Okay, now Ft is constant. Ft is constant. Then also V is constant. The force applied to the drive is also constant and the velocity is also constant. Now we can write Ft multiplied by V. The force multiplied by the velocity becomes, you can write Ft means, I'm sorry, V means Ft omega m into r. Okay, you can write this. Now Ft into r means torque. That is the load torque multiplied by the omega m is constant. Okay, nearly constant speed, constant power will be achieved. Nature is hyperbolic nature. Okay, this is all about the nature and classification of the load torques. They have to be applied during the latter stage when motor drive dynamics will be studied. Next, I am coming to steady state stability of the electrical drives. This is very vital. Steady state stability. Steady state stability. If I consider two kinds of motor load arrangements, graphical representation, if I draw say this is the motor torque and say this is the load torque. Okay. Now obviously at steady state operating point, load torque and motor torque is same. That is, this is the steady state operating point A. This is the point. A is the steady state operating point. Okay. And another case, this is not TL. This is the motor torque. This is the load torque. Okay. Now this is the motor torque. Say this is load torque. Now in this case, this is the operating point. Say B. These are the 2 points where the motor is operating. Now, any kind of deviation in speed from this steady state operating point, that is, this is the steady state operating point, okay, or steady state speed. I am withdraw this character. This is the better. Now this is our steady state operating point. Okay. Now any deviation in speed from the steady operating point, what will happen for the first figure I am considering? Say speed is decreased. That is, now motor is operating at this point. That is the speed. You can write omega m minus delta omega m. Okay. Then what will happen? This becomes the load torque and this becomes the motor torque. Okay. Now for point A or figure, first figure, if decrease in speed offers load torque is or speed, decrease in speed, say omega minus delta omega, omega m. What will happen? Motor torque becomes greater than the load torque. Okay. Then what will happen? J d omega dt becomes positive. becomes positive and motor accelerates and return back to the point A. Okay. Now for this figure, if decreasing speed from the operating point, say at this point, this becomes the motor torque and this becomes the load torque. Okay. তাহলে decreasing speed at omega m minus delta omega m. This is the omega m minus delta omega m, this point. Okay. Motor torque becomes, this is the motor torque Tm and this is the load torque Tm less than TL. That becomes J d omega m dt becomes negative. Okay. And motor decelerate. That is, speed will be again decreasing. Now, if I consider the increment in speed for the first figure, say this is omega m plus delta omega m, this point. Okay. Now, what is the motor torque? This point is the motor torque, this point is the load torque. Okay. Now, at omega m plus delta omega m, what will happen? Motor torque, this is motor torque, is the less than the load torque. Then J d omega m dt becomes negative and motor decelerate and again return back to point A. And for this operation, say speed is increased at this point. Now this is the load torque, this becomes the motor torque. Okay. Then motor torque is greater than the load torque, that is at omega m plus delta omega m, motor torque is greater than load torque. Okay. Then J d omega m dt becomes positive. That is, again motor speed is increasing and it not return back to the previous operating or stable operating point B. Now this first figure for this kind of motor load arrangement, we can easily say this is the stable motor load operation and this point is unstable. Okay, any deviation from point A will be returned back to the point A because of the motor load dynamics. And for point B, if any deviation from point B will drive the motor from far away from the point B and the operation becomes unstable. Okay. Now, if I again alternative approach method, that is mathematical method, alternative approach to find out the stability for steady state stability. Okay, now at equilibrium point, what we have concluded, that is, from these figures, these two figures, we can conclude from these two figures, we can conclude for stable operating point of operation, for stable operation operating point, any deviation in the load torque greater than dt m by d omega n. Okay. Now, this is the equilibrium point of operation. Now, any deviation from this point, say if I consider these characteristics, so this point we can write Tm plus delta Tm, and this point we can write TL plus delta TL. Okay. Now, any deviation of speed consider at speed omega m plus delta omega m. Motor torque becomes Tm plus delta Tm, and load torque TL plus delta TL. Okay. Now, what we can write? We know T equals to TL plus J d omega m dt. Now, I am writing same equation, Tm plus delta Tm will be equals to TL plus delta TL plus J ddt of omega m plus delta omega m. Okay, that is Tm plus delta Tm equals to TL plus delta TL plus J d omega m dt plus J d delta omega m dt. Okay. Now, what we can write? We know that motor torque is equals to load torque plus J d omega m dt. Okay, that is, if I write TL plus J d omega m dt plus delta Tm plus delta TL J d delta omega m by dt, right? Now from which we can cancel out these terms. That is, remaining terms are delta Tm will be equals to delta TL plus J d delta omega m dt. Okay. Now, for any small perturbation of the speed torque characteristics, we can consider as linear. For any small perturbation, assume torque speed curve is linear, or better to say curve is straight line. Okay, that is what we can write. We can write delta Tm equals to dTm by d omega m delta omega m, and same thing for the load, that is delta TL equals to dTL by d omega m delta omega m. Okay. Now if I put these two values in the previous equations, that is delta Tm, we can write dTm by d omega m delta omega m plus equals to dTl by d omega m delta omega m plus j d delta omega m dt, right? Then dTm by d omega m minus dTl by d omega m whole multiplied by delta omega m equals to j d delta omega m by dt. Okay, that is, we can write j d delta omega m by dt plus dTl, if I take the minus sign the outside, by d omega m minus dTm by d omega m equals to 0. Okay. Now this is the first order linear differential equation. Okay. Now this becomes first order linear differential equation. Then what we can write? d delta omega m by delta omega m will be equals to minus 1 by j dtl by d omega m minus dtm into dt. Now if I take the integration, what becomes? That is ln delta omega m. You can write that is minus 1 by j dtl d omega m minus dtm d omega m into t. Okay, is d omega m into t. Okay, that is delta omega m t plus c. Say that is the integration constant, initial value. Then we have to first find out the initial condition at t equals to 0. At t equals to 0, the system is operating at a stable point, that is no deviation of speed. That is the initial deviation of speed. At t equals to 0, delta omega m can be considered as delta omega m equals to delta omega m 0. Initial speed deviation. Okay. From this, we can write at t equals to 0, that is c equals to ln delta omega m 0. Now if I put this value ln delta omega m by delta omega m 0 equals to minus 1 by j dtl by d omega m minus t. Okay. Now delta omega m will be delta omega m 0 e to the power minus 1 by j dtl by d omega m minus dtm by d omega m t. Okay. Now, for the steady operating conditions at if delta omega m approaches to 0, obviously it is only possible when t approaches to infinite. Okay. Now the exponential terms, when it is possible, the exponential terms must be negative. When exponential term will become negative, that is dTL by d omega m is greater than dTm by d omega. Okay, this is the criteria for the equilibrium point of operation. And from the graphical representation, we will also get this. Okay.